bit further with understanding nuclear structure. We're going to talk about an atomic structure overall. We're going to talk about how the periodic table can give us information about the structure of an atom and concept of isotopes. Um, if you flip to your periodic table and your reference tables, any of the element symbols are going to look like this. And this is what we can learn from this symbol. The top left-hand corner tells us the atomic mass. This is a little bit different than the mass number, which we're also going to talk about today. This is actually an average of all the sodiums that are out there, which is a different concept we'll talk about later in the unit. We have the atomic number, and this tells us our number of protons. The number below that is our electron configuration. Electrons, as we mentioned, live in these things called energy levels. So this kind of gives us a little bit of an idea of what energy level our different electrons are in. What you'll notice is that the number of protons and electrons should be equal in an atom. So we have 11 for our atomic number. 2 plus 8 plus 1 gives us 11. So we have 11 electrons. Up here we have something called the oxidation state. This is the charge that an ion will have. Don't get this confused with the concept of nuclear charge. It's a very different idea. I think a lot of students see them and they think that it means the same thing, but it doesn't. We'll talk about ions and that kind of stuff later. So the nuclear charge of a sodium atom, which we talked about nuclear charge before, remember is based on the number of protons in the atom. So this is going to be positive 11. So this is something called isotopic notation that we're responsible for being able to read and write in. You have a large number for the element, or a large letter for the element symbol. You have too small or a top number that will be the mass number, which will not be that decimal number you see in the periodic table. It'll be a whole number. And the atomic number, which is going to be the number of protons. You're actually allowed to leave that bottom number off, and we'll talk about why in a minute. So looking at this symbol, we see the letter S, which is the symbol for sulfur. That should also align with sulfur's atomic number, which is 16, and it does. So if you go to the periodic table, you'll find that sulfur's number is 16. It shows us we have 16 protons. Our mass number given by the top number is 33. So to determine our number of neutrons, we're going to subtract these. So 33 minus 16 is 17. One thing to notice, if you actually do take a quick second and look at sulfur, sulfur is actually given as having a mass of 32.06. This is actually because that's an average of naturally existing sulfurs. This particular atom of sulfur happens to have a mass of 33. So we'll kind of talk about where that comes from as we go through the unit. Our next one, we have bromine. Which has 35 protons, hence the atomic number 35, and that should match up with what we see in the periodic table. Our mass number is given as 80. Which means we have 45 neutrons, which we get by subtracting them. Now the next one, I threw a little trick at you. I gave you molybdenum. I didn't give you that bottom number. So you're saying, okay, I know my mass number is 95. You're actually not required to write that bottom number. If you go to the periodic table and find molybdenum, you'll see that it's number 42, which means you can fill in a 42 down there, or you can leave it off. It's assumed because people know that since it's molybdenum, it has to have 42 protons. So for my number of neutrons, I'm going to subtract those and get 53. We'll be using isotopic notation a lot throughout the year in some different units, so it is important that you understand how to read these symbols. Alternatively, you can also write them a little bit differently. You can write S33. You don't write S16. That's assumed with that. Sometimes if you're typing something that's a little bit easier to write it that way, you can also write out sulfur 33. So this is a common way of showing what the element is, which lets people know how many protons there are, and the mass. So you can do PR 80. showing the mass afterwards. This is especially useful if you're typing and you really don't want to bother making the symbol, which can be a little bit annoying. So if we check out these two atoms, we're going to notice these are both carbon. And I can prove that by the fact that carbon's atomic number is 6. So if you count your protons in each of these, we got 1, 2, 3, 4, 5, 6. And if you count the protons in the bottom one, we have 6 there as well. We have 6 electrons in each of these because they're atoms. So our protons have to equal our electrons. The difference between the two of these is the number of neutrons. So in carbon 12, carbon with a mass of 12, we have 6 protons, same as in carbon 14. In each of these, we have 6 electrons. The difference is in the number of neutrons. 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4, 5, 6, 7, 8. So if you subtract these like we did on the last page, you say, okay, I should have 6 neutrons here. I should have 8 neutrons here. Lines up with our picture. These two carbons are what we call isotopes of each other. So you have learned about carbon 14, especially when you talk about in earth science, radiocarbon dating. Carbon 14 is what's called an isotope of carbon that is unstable and will decay by giving off beta particles. So most of the carbon that we're made up of is carbon 12, luckily, which is stable and sticks around for a long time. So what makes these two similar, specifically, is that they have the same number of protons. And they have a different number of neutrons. They also happen to have the same number of electrons, but that's just kind of more of a consequence of having the same number of protons. Not quite as important. So isotopes are when we have different atoms of the same element that have different masses. The reason that they're the same element is they have the same number of protons. The reason they have different masses is that they have different numbers of neutrons. So remember, because these are atoms, that means their protons do equal their electrons. So it's kind of a consequence of their numbers of protons being the same. A few sample regions questions for you. Table below gives information about the nucleus of each of 4 atoms. If you'd like to pause the video for a minute to try these questions quickly, we will put the answers up in just a moment. I apologize, this is not in your packet, so you have to kind of look at what's on the board. So in question 1, if we want to know how many different elements are actually present there, the number of neutrons doesn't really identify elements. So in the number of protons column, we see that we have something with 6 protons, something with 7 protons. So we actually only have 2 different elements shown in that table. We have a lot of different combinations, but those are just really isotopes of the same element. What is the mass number of a carbon atom that contains 6 protons, 8 neutrons, and 6 electrons? So what this is asking for is the mass number. Mass number is technically number of protons plus the number of neutrons. So 6 plus 8 is 14. Again, that's different than that average that you're seeing in the periodic table because that's based mostly on carbon 12. This is talking about an individual isotope or an individual atom of carbon that does have that combination of protons and neutrons. What can be determined if only the atomic number of an atom is known? Neutrons are not told to us by the atomic number only. We would have to also know mass. The next one's tempting, number of protons only. But let's check out our other ones. Total number of protons and neutrons. Again, we can't know neutrons. Check out choice 4. Total number of protons and electrons. Since we know that we have an atom, protons equal electrons, actually choice 4. We can know our protons and our electrons.